Okay, so can you hear me? Yes? Okay, so we'll start. Can we? Okay, so the chief say we can start, so we're going to start. I'm Yann Orlarey. It's not, okay. I will stay seated because I will do some live coding, you know, the thing that never works, but I will try. Si tu veux, je préfère m'approcher un peu du micro. Je pense qu'il est trop... Okay. Bon. On the back, can you hear me? Fantastic. Okay, so the title of the talk is From Combinatory Logic and Lambda Calculus to Faust. So maybe you know, if you know Faust, that it's the 20th, well, the 20th, how do you say 20th? 20th anniversary for Faust. And thinking about what I could discuss during this keynote, I say, okay, why not speak about the formalism that inspired Faust. So thanks for the organizers and Romain and Laurent for inviting me. It's not my first time in Saint-Étienne. I live quite close from Saint-Étienne. Okay, so I will start with a quotation from John Bacchus. So John Bacchus is famous because, who knows John Bacchus? Yeah. Okay, well, my talk is going to be a little bit computer science. Okay, so I will speak of formalism and computer science. So John Bacchus is very well known because it's the inventor of the Fortran programming language. And it's also the inventor of the so-called BNF notation, Bacchus-Noor form, which was first used for the definition of the syntax of Algol, and at the end of the 50s. And before that, surprisingly, there was no technique to specify the semantics of a programming language. So people were explaining with words and sentences how to use what was the syntax. So John Bacchus introduced a formal way to describe the syntax. And because of Fortran and because of the BNF notation, he received the ACM Turing Award in 1977. And on this occasion, he published a very interesting and very inspiring paper called Can Programming Be Liberated from the von Neumann Style, a functional style and its algebra of programs. And this paper had a lot of influence on many people that later started projects in functional programming and designing functional programming languages. And if in this paper he was discussing, in particular in the first half of the paper, a language called FP, like functional programming. And if you look at the examples, you will see that it has a lot of similarity with Faust in terms of syntax. Well, Faust has a lot of similarities, was influenced by FP in its design. So the quotation from John Bacchus is, conventional programming languages are growing ever more enormous, but not stronger. Inherent defects at the most basic level cause them to be both fat and weak. And if you design a programming language, you feel a pressure, for example, of users. You are super happy to have users, they have demand, etc. And there's a lot of pressure in adding layers and layers and layers on top of your programming language. So it's a natural tendency. And I think that John Bacchus was also part of the committee for Algol, and he had the strong feeling of this effect of designing by committee where everyone wants to add its own feature, etc. And also, I think that quite surprisingly, computer science is a little bit it's a very conservative field in somehow, and some technologies, some ideas take a long time to diffuse, to penetrate, to sink in. Okay, thank you, Miller. So, for example, there is a very good example, which is when I discovered that, I was very surprised, is the fact of recursion. So we take for granted to have recursive programming languages nowadays, but that was not always the case. For those that don't remember what recursion is, here is an example of, so you see a genealogic tree, and let's say that you want to define the concept of ascendance. The traditional definition that you can find quite easily is my ascendants are the person to whom I'm related in the ascending line, including my parents, grandparents, great-grandparents, and the like. So it's an example of completely non-recursive, quite verbose definition of the concept of ascendants. So here is the recursive definition. My ascendants are my parents and their ascendants. So you see immediately that recursion provides a kind of elegance, and it's a quite minimalistic system to define things. So it's a super powerful tool in many cases. But it turns out that I have this very interesting little book by Daniel Baron, published in '68, about recursive techniques in programming. And it's very surprising when you read this book, the fact that it tries to advocate the usage of recursion, because at that time, recursion is widely regarded at present as an interesting frill in a programming system. There is also considerable prejudice against it. And so, and the aim of the book is, I hope that this book may do something towards the acceptance of recursion by showing that it is neither complicated nor esoteric. So I don't know for you, but for me it was a kind of shock, because it was so obvious that recursion was something very important in programming languages that I never thought that it took the 90s, Fortran 19, to have recursion in Fortran, for example. Until then, it was a non-recursive programming language. But it turns out that, and we will see that recursion, even super interesting and super important and super elegant, is not essential. And you have some formalism where you can define in a non-recursive way recursion. And I will show you how you can do that in lambda calculus. So somehow this talk is about what is the essence of a programming language. When you design a programming language, at some point, you have to try to figure out what are the important features of the programming language, what are less important. And so you have to have a notion of essence of this programming language. Obviously, if you look at modern programming languages like, I don't know, C++, for example, it's very difficult to find what are the essential points in this language. There are so many features in the language that it's super difficult to find that. So the idea here, and it was also the research work we were doing at Gram at that time, was to look at programming languages, so to speak, that were invented before programming languages and before computers. And this formalism that I will present, for me, is very elegant. So let me define what I mean by elegant. Is the fact that you have very few concepts, but by combining all these few number of concepts, you can create very complex things. So for me, elegance is the combination of expressivity and simplicity, so to speak, at least for programming language. I agree this is a very subjective way to think of elegance in programming languages, but well, this is the choices we did. So there are three formalisms that I would like to present. The first one is rewriting systems. It was invented in the beginning of in 1914, and you will see it the most natural way. Then you have combinatory logic, invented 10 years after, and you will see it's a super radical way to do computation. And then lambda calculus, which is my favorite, so to speak, and which is, for me at least, the most elegant one. So I would like to go through these three formalisms and tell you how they more or less inspired the design of Faust. Okay, so maybe I can start with a quick demo of Faust for those that don't know the language. So I'm going to, I need to put my glasses because I guess you can't see anything, right? Can you read? No. Okay, so is it good? Okay, anyway, it's just to show you a little bit how things work. So I'm going to write a program that do a noise generation in Faust. Okay. You can see here the block diagram generated by the code. So you see the noise generator here, which is basically a pseudo-random number generator in between -1 and +1. Now, if we listen to this, we will have a noise at full level. So I'm going to add a volume control. So I'm going to copy this piece of code here. So basically this is what I'm copying here is a kind of amplifier. And I use the colon sign to say that I want to combine the output of the left-hand side expression to the input of the right-hand side expression. So this colon sign is like the pipe operator on Linux, for example, and on Unix, sorry, and it was a source of inspiration also. Okay, sorry, and so it's like the pipe operation on Unix, and it's a way to combine audio circuits, so to speak. So I'm going to combine with this, and now we can listen to this noise generator, and we have a control of the volume. So the noise is going only on one loudspeaker, so I'm going to split the signal here and send it in the two loudspeakers. Voilà. Okay, now I'm going to replace this part here with something more evolved, so to speak. I need my glasses. It's a kind of resonator. Okay, and the idea here is more or less to simulate a wind. So the strongest is the wind, the highest is the pitch also of the signal. Okay, it's not a very fancy program. It's just to give you an idea of how Faust works. So, and the important part is the fact that you see you combine things you do essentially, you program by function composition, so to speak. And the colon sign, sorry, is one of the 5 operations for doing function composition in Faust. And this is very related to the combinatory logic and also to this FP language of John Bacchus. What's nice in Faust is that once you are happy with your program that you prototype, you can export it to, for example, an Android application. And so you launch the compilation, the code is sent to a remote compilation service, and at some point you will receive a QR code, and you can scan the QR code with your Android phone and have the application that run for you. Because it takes time for the code to be compiled. Here I have the application on my phone. And because you can map all the sliders and the buttons on the accelerometer, then it's easy to have a gestural control of your application. Okay, again, this is a super simple example here. I need to stop it. Voila, so at some point he will deliver us the QR code, so I'm just quitting that. And I'm coming back to the slides. So this was the Faust quick demo, so you don't get lost. So let's start with rewriting systems. As I said, it's the most natural way to define this kind of computation, so to speak. Rewriting systems were invented, or at least very formalized, by Alex Tew, which was a Norwegian mathematician. And so basically you describe a transformation by saying, if you see that, you can replace it by that, etc. And so you give a set of transformation rules. And so here is an example. You see you have a starting point with white and black coffee beans, and you have rewriting rules. So you say, if I have a black and a white coffee bean, I can replace it with a black coffee bean. If I have a white and a black coffee bean, I can replace it with a black coffee bean. And if I have 2 black coffee beans, I can replace it with a white coffee bean. These are the rules. So then, starting from the initial position, you can apply these rewriting rules. So for example, you can apply rule number 1 here and replace that with this black coffee bean, apply again the rule, etc. So, and at some point, you reach what is called the normal form, a form where no more rules can be applied to transform this. So you are at the end of the process of doing all this transformation. What's interesting here is that here we reach this normal form, but from the same situation, by applying the rule on a different position, here you can, starting from here and then here, you reach another normal form where all the beans are white. So this is an important properties in rewriting systems. Some are non-confluent. You don't reach a single possible value, so you cannot really use them as a computation tool, so to speak. And some others are confluent. And in this case, you can think that the green position that you obtain is somehow the value of the initial position, because doesn't matter whatever path you take, you end with the same value. And some rewriting systems are not terminating, so a Turing-complete language is non-terminating by definition. Who has ever seen this book? the algorithmic beauty of plants. Oh, so it's a super nice book about using rewriting systems to grow plants, so to speak. And there are very spectacular images in the book of completely artificial plants described with this kind of rewriting rules. So, for example, here is the modeling of Micellis muralis. Oh, everybody know Micellis muralis? No? I don't remember either. Well, I think it's a very common plant, but anyway, so this is the omega here, the starting point, and these are the rules that you can apply to do the transformation. So let's see what happens. So you start here, and here you see the evolution of the plant as every time you apply the rules again and again. And at some point you start to have flowers that emerge. And then the plant is growing, and you reach the final position, so to speak. And here the same thing, but with a 3D model of the plant. What's interesting is that if you are able to generate a nice, if you take a plant, and if you have a model of that plant, and if the simulation of the plant gives something that looks like the original plant, somehow you capture something of the growing process of the plant, even if in a very artificial or computer science way. Okay, so in Faust, we can use this idea of term rewriting using the pattern matching feature of Faust. So I would like to show you how to grow an FFT circuit based on a model defined by Julius Smith. And this type rewriting feature of Faust, in particular the pattern matching Faust, is due to a collaboration with Albert Greff, which is a German mathematician and who developed several languages based on pattern matching. So let me show you how we grow the FFT in Faust. So, oops. I copy this code here. So basically, this is the code of the FFT. So you see, it's super. Oh, syntax error. Why that? Okay. Sorry, I'm going to grow that. Even starting from. Okay, I need to import the standard library. Okay, so we don't want to run it, but we want to look at the resulting circuit. So here it's an FFT with just one point. So because we need to use complex number, we simulate these complex numbers with two cables. Here it's an FFT of 2. So you see emerging the pattern, and this pattern is described by these rewriting rules here. So to make an FFT of n, you need to make two FFT of n divided by 2. The first one go into a standard bus, and the other one go into this twiddle odd stuff, which is a multiplication with sine and cosine. So what happens if we use 4, for example? 8, 16, 32. So you see that in Faust, we generate circuits, so to speak, but using the algorithmic power of a functional programming language. And this is possible thanks to the fact that we have an algebraic approach. We don't have how to describe how to connect all the things together. We don't have to rely on external programming language to do all the connection. It's really based by the fact that we use an algebraic approach. Okay, so this was for the application of term rewriting in Faust. Now I can come back to my slides. Another application of term rewriting, which is also very well known, is the fact of using term rewriting, for example, to do the game of life. So you have a set of rules, and instead of applying them on a string, you apply them on a grid, but that's the same principle. Let me show you a very nice video of Game of Life. So who doesn't know Game of Life? Okay. So basically you put dots, and some dots are alive, some will die, and some new dots will born. Huh? Not? Will appear, yes, okay. So for example here, this particular configuration has the particularity that when you start, it moves. So it's a walker. Okay. So what can you do with that? It's a surprisingly simple system that is known to be Turing complete. So just an illustration of to be Turing complete, to have the expressive power of a computer, can take very little and very simple systems. And I think it's important to know that if you want to design a programming language, because you can design very, especially for creative works, a very special programming language knowing that. Let me show you a nice video of the Game of Life. And you will have a surprise, so to speak. So this is the Game of Life running. So it's a huge Game of Life. Maybe you start to understand what you are looking at. So it's Game of Life in Game of Life. I just can't imagine how someone could, yeah. So someone invented the square here, the mechanism of the square, but just very impressive for me. So it's a kind of visual proof that you can write Game of Life in Game of Life. So it's a surprisingly simple system with huge implication, and there are generation of mathematicians that studied the Game of Life. And if you know the book of Wolfram called A New Kind of Science, it's all about about cellular automatas and how you can model the physics of the external world. So basically, his theory is to say, okay, we are living in a cellular automata. Well, we don't have to believe him, but this is what he says. Okay, so this was for Game of Life, and now we can switch back to combinatory logic. So, yes, something to say. Who knows the Morse sequence? Okay, Stefan, good. Tew and Morse invented a sequence called the Tew-Morse sequence, which is a sequence of 1 and 0. So, and you can define that using a term rewriting system. So imagine that whenever you see a 0, you replace it by 0 and 1, and whenever you see a 1, you replace it by 1 and 0. You start by 0, and you apply these rules. And you create a sequence which is super interesting because it any subsequence never repeats more than 2 times in a row at any level. Every pattern will appear an infinite number of times, but every pattern will never repeat 2 times, more than 2 times in a row. So if you use that to code some musical parameters, it gives you, it's not random, but it's super interesting because it has structure and at the same time is never exactly the same. So there are interesting applications for the Tew-Morse sequence. Okay, so combinatory logic, the most radical one. So it was invented by Moses Schoenfinkel in the 20s. And the idea, the radical idea of Schoenfinkel that we should get rid of the concept of variable. We should not use variables at all. It's not a fundamental concept, which is strange because we are so used to define functions. Like, for example, if I want to define the distance between 2 points, I will typically define some function like this, and I will use formal parameters, variables for that. So and when I use it, basically it's a way to say where all the parameters have to go into the formula. So this is important. You can see that the use of a variable, it's a way to route information from the input to the formula, so to speak. And this is the mechanism that combinatory logic will use. So the first thing that Schoenfinkel showed is that you can do multiple function with multiple variables. You can transform them as function with one variable. Basically, you transform a parallel, how do you say, a parallel distribution of the arguments of the function into a serial distribution of the argument of the function. And this now is very well known as curification. And this idea, which is super old, takes ages to reach the programming languages that we are using today. So in Haskell, for example, and I think even in JavaScript now, you can curify functions, so to speak, transform them into a function that takes the first parameter, return the function that takes the second parameter, that return the function, the third, etc., until you reach a form where you don't have need of any more parameter to do the computation. And so this principle invented by Schoenfinkel was later rediscovered by Haskell Curry. And it's why it's called curification. So in Faust, we use heavily, we don't need curification because we have partial application. But it's supernatural to use that. For example, let's say you have a transposition operation. It's supernatural to pass for example, you pass 12 because you want to transpose of 1 octave. So you specialize your tool. So you have a tool with all the parameters, and then you pass not all the parameters. You say, okay, I just want to transpose by 1 octave. I just pass 12 as a first argument. And then the resulting function will wait for the sequence, the MIDI sequence, for example, to transpose by 12. I'm not sure I'm clear, but it's a super interesting feature in programming languages. Again, an idea very old that takes a long time to spread into normal programming languages. But the most spectacular result of Schoenfinkel is that you can do everything with combinators. He first proposed 5 combinators, which are, again, way to route parameters to the place where they need to be used. So in the first version, he proposed these 5 parameters, these 5 combinators. Then he discovered that you don't need the phi one. You can just use S, K, and I. And then he discovered that you don't need I because you can express I as S, K, K. And here it's what happens if you apply S, K, K to X, for example, and you end by X, so it's a proof that this is equivalent to I. Okay, so so you can express all the computation with just 2 functions and the idea of application. So this is very radical, I would say. And you can even create a special, which is not exactly technically a combinator, but a single function that replaces, and you can do everything with a single function. And so this idea is used to implement functional programming languages. For example, Turner SK machine. It was heavily used in the FP programming language by Bacchus that I mentioned at the beginning, and it leads to a kind of called point-free or tacit programming style, where you don't have to use variables, you don't have to give names to things. You route them, so to speak. So this is used in Faust. For example, if I want to define the RMS value of a signal, I can combine the square of the signal, a mean, and then a square root of the signal. And okay, here I need a variable. I could have avoided that, but this kind of programming style where you don't give names to signals is very particular to Fast. I know that some people doesn't like at all this approach, but I think it's interesting. Now, let's switch to lambda calculus, because I have a demo to show you. So lambda calculus is the latest. Alonzo Church invented that. In the first, well, he tried to replace sets by functions to do a kind of new foundation of refoundation of mathematics, but it ended with paradoxes, like the famous paradoxes you can have with naive set theory. But now the lambda calculus is a theory of what mathematical functions are. And again, it's very elegant because everything is done using 2 concepts. And I will try to explain these 2 concepts in a non-mathematical way. You can do a presentation of lambda calculus like this slide, which is a classical presentation of lambda calculus. But you lose, in my opinion, an important intuition of what abstraction really is. Okay, so let me skip this and go into this presentation here. Let's say you have sentences, like today it will be sunny. the elements that you are using in lambda calculus don't have to be called X, Y, Z, etc. You can give arbitrary names. So let's say you say today it will be sunny. An abstraction is the idea of making variable some of the elements that you have used in the sentence. For example, I can make variable the fact that it was today. So lambda calculus is essentially having search and replace in a text processor, but as two separate functions. You have the search one, but you don't tell by what you are going to replace, and then the application operation, which is where you do the actual replacement. And so here I make variable today it will be sunny, and then the other element of lambda calculus, the reverse, so to speak, of the abstraction is the application, the fact that you want to use this function. So now you can apply this lambda today it will be sunny to tomorrow. And what happens in this case is that you have what is called the beta reduction. Just a way to say that tomorrow will replace the variable part called today. So the result is that today is replaced by tomorrow, so we have tomorrow it will be sunny. So this is a function. That's all what you have in lambda calculus. And from that, such a simple system, you can build everything. You don't have numbers, for example, you don't have booleans, you don't have recursion, and you don't have data structures, and you build all this concept from this super simple two ideas, abstraction and application. Okay, so here are definition. I will make a demo of this in a moment, but philosophically what is very interesting is that in lambda calculus you don't have numbers, you just have functions. So when you want to implement numbers, you need to find what is the function of a number. And what is written here is that the function of a number is, for example, to iterate a function on some argument. So for example, here you see you have a lambda. We say, okay, we make variable a function, we make variable a number, and we return the number. So basically, we iterate 0 times the function on the number. If 1, for example, we have a function, we have a number, an object, and we iterate 1 times the function. 2, we iterate 2 times the function. Then it means that you can create the successor of 0, and you can implement all the numbers using this approach. The important point is the fact that you don't see things are what they are by, how to say that in English, because of how they behave, so to speak. They are not per se numbers. They are not per se booleans. It's because they behave in a certain way that you can consider them numbers and booleans. Okay, and this is recursion. I'm going to, okay, skip that because time is running. Example of abstractions in Faust. But I will show you a non-classical use of lambda calculus called the graphic calculus. So I'm going to make a demo. And for example, I'm going to, you see this object? I'm going to program this object in front of you without using a programming language, either graphical or textual. Just using the power of lambda calculus. If I manage not to make mistakes. So let's, no, sorry, not this. Okay, this is the application that I'm going to use. Okay, so here you have colored cubes, and what you can do is basically take a cube, You can combine two cubes together. You have several ways to, with this pop-up window, you can combine two cubes. And for example, when you combine two cubes on the horizontal dimension, the two cubes are compressed so that the result is always inside the cube, okay? Here you have an history of all the things that you do. For example, I'm going to do this and this. Now I'm going to take in the history this and put this in front. Okay, so basically I did this kind of damier. How do you say damier in checker or a damier? Checker? No, okay. Well, this kind of object here. No. Okay, it doesn't matter. Well, you create this kind of object here. Okay. Now I'm going to, I want to capture this idea of placing two blocks in this particular way. So how can I do that? By making variable the white and blue cubes that I have used. So I can do that by, I take the white cube here, and here you see there is something called abstract. So I'm going to abstract the white cube. So now it means that the white cube inside the object is a variable white. It's a parameter, so to speak. It's still white, but it's a variable white. It can be replaced by something else. So for example, if I apply this now to invisible, and then the white has been replaced by an invisible cube. Okay. So now I can also make variable the blue that I have used. Okay. Now I have a function with two arguments that can, from the lambda calculus point of view, it's a function. So I can apply it to, I don't know, green, for example, and invisible. And then again, I can apply that to this to invisible and this to this object here. Okay, I have created this structure. Now, I'm going to show you how you can implement a recursion, which for me it's the famous Y combinator. Who knows the Y combinator? Okay, few of them. Well, in my opinion, it's one of the most beautiful formulas, so to speak, in computer science. So let's apply, again, you see when you apply an abstraction, there is this beta reduction. The variable part is replaced by the argument. If I apply green to green, nothing happens because green is a concrete object, it's not an abstraction. Now let's apply white to green, apply to green. Nothing happens because, again, white is not an abstraction. Now I make variable the green, and I apply this object to itself. So I apply this object to itself. So here the green applied to green will be replaced by this object applied to itself, etc., etc. So what we will have is white applied to white, applied to white, applied to white, etc. Now, if I want to capture the idea of applying something to itself indefinitively, what can I do? You cannot compete, Stefan. So. Okay, but the solution obviously is to abstract white. And this is the Y combinator of lambda calculus. So let's do a complex object with that. So I'm going to take blue, white, green. I make variable green, and I do a recursion on that. Okay. Now again, I take again this object. I put the green on the other side. I make variable the green, and I do a recursion. Now I combine these two objects. So you have a kind of accelerando of 2 colors. Now, I can make variable the white and the blue cube that I have used for that. Okay, I create a function like the checker before, but there is something else that we have used to make this object. We have used the idea of putting the objects together horizontally. And we can also abstract this idea. So here it's the concept of putting 2 things together horizontally. So I'm going to make that abstract. And because this is abstract, now I can apply to a different way to combine things. For example, to combine them, let's copy that. To combine them vertically. And we change the shape of this object by doing like this. And then I want to do that on the deep axis. And so these are my 2 objects. Now I'm going to make a complex object. Okay, let me prepare my, okay, so I start with this one. And again, this one here. Okay, here, for example, everything seems to be white, but you have 2 kinds of whites. You have the abstract white and the concrete white. And I apply that to blue, and here's what we obtain. So I'm going to duplicate these 2 objects. Now I'm going to apply this, and apply this. And then I apply this, and this. Okay, so this is the object that we obtain. Okay, so it's a recursive object in the three in all the dimensions. Note that you can, let's do a simple function, the identity function. I take a color and I make variable this color. And now I'm going to make also a function that makes something invisible. I abstract blue into invisible. Since there is no blue into invisible, I create a constant function. Let's store this here. Now I can combine these objects, for example. Okay, so this object is made of identity function and make invisible functions. If I apply this object to this cube here, there is an extension of the beta reduction because I'm going to apply something which is not an abstraction, but a construction of abstractions. And in this case, is going to slice this object, so to speak. So the part that were with the identity function are now visible, and the others just disappeared. Okay, I should not forget to skip that. Okay, let's do another object now. I take white. I put 4 whites in horizontal construction. Now I take red, white. I put them together. And now I do the same thing for the red. And I put it here. So now I can do like this. Up. Now like this. Okay, I store these elements here. Up. So, Can you guess what I'm doing? Okay, so this is this cube here. Now I can make variable again, the red and the white color that I have used. And for example, I can I apply that to white and to invisible, for example. And I apply again this to this, and again this to this, and I can create the variant of the Sierpinski sponge, so to speak. Okay. So, but the interesting point is that I can, for example, I can use identity function and make invisible function to fill this object here. So the point, maybe I'm not very clear, but the point is that because the objects here are these cubes, and because the programs that you build, these abstractions, are also cubes, it means that you can place them in space and do complex things by the fact that you place this functionality in space. There is a kind of recursion of the tools on itself, so to speak, like in Lisp, where you can have programs that generate programs because all the programs are Lisp, etc. So you can use all the power of Lisp processing to generate Lisp programs. And here you have the same phenomena. So for example, if I fill that with where is the identity? Okay, I make invisible here and identity on the center. If I apply this to this, here's the result. But I can also take this object here, make variable the blue and the white, and then I can replace the cubes of color with functions. So now you have, I think I should stop, right. You have identity function here, and if I apply this this object to, let's say, this one, for example, we are going to creuser, what do you say? To dig in every function that makes invisible, we make a hole into the object. But you see that the way to make the hole is, it's a fractal object, so to speak. So the code, if I would speak in terms of code, is it's a fractal code. Okay, so well, I think it's difficult, but if I retrace this object, I can, it's not exactly what I promised you, which was this object, but this object without the green, but the same object. Okay, I should stop here the demonstration of the graphic calculus. Just mention that we applied this idea a few years ago into the LOD music environment. So instead of cubes of color, we were manipulating notes, but the compositional processes we were manipulated were also musical objects, so it was easy to compose in time music composition tools, so to speak. Okay, just to end on the concept of abstraction, because I think it's a super important concept. We tend to see abstraction as something that comes from the top, so to speak, by the language. But you see that actually abstraction can come from the bottom, and you can think of abstraction as a process of forgetting non-important things, so to speak. And when you start, I don't know if I ask you to define what is a dog, it's probably difficult for everybody to say what is really a dog, but we recognize dog very easily because we have learned to what were the important features, so to speak, of a dog and what was neglectable from the dog. And so abstraction is super important, and it's important to think that there is not something that is abstract. There is something that is more abstract than something else. And abstraction is a process also. And unfortunately, in all our programming languages, but this graphic calculus and LOD, abstraction is not a process. You can define abstractions using variables. But here you see an example where you define abstraction from concrete examples. So it's a kind of programming by example done by making variable. You start to do something, and at some point you say, okay, let's, I have this construction. What happens if I make variable the theme, the musical theme that I have used for this construction? And what happens if I apply it to something else? And it's a very powerful way to do things. So conclusion. At the end, what is left? Well, once you remove all the fat, nothing is left. You don't have numbers, you don't have booleans, you don't have recursion, you don't have data structures. The only thing that remains is the idea, the general idea of function. And everything can be built on top of the notion of function, which is quite surprising when you are so used to have all these features in programming languages to discover that everything can be rebuilt. I'm not claiming that it's convenient and practical to use church numbers, but it could be interesting to keep in mind that numbers can be functions. And to my knowledge, no programming language uses that. Okay, so this is the end. Thank you.
Well, thank you very much, Yann. Just before you guys leave, I just want to say two things. So for lunch, it's just like yesterday. So you go to the restaurant. Try not to go all at the same time. There's wine on the table. There's rosé and white wine in the fridge, and it's cold this time. And there's beer too. For those of you who are waiting to go for lunch. And this afternoon, there's going to be two parallel sessions, right? So one session is going to happen here in this room at 2 p.m. The other session is a session in French. It's the Young Researcher session, and it's happening at the Fabrique de l'Innovation, which is the building next door. If you don't know where the building is, you just go on the program. There's a link on Google Maps to find the building. You should be able to see that. Anyway, enjoy lunch. Thank you.